All right, this is a hard one. We got a tough Lewis structure that we're going to build. And then we're going to minimize the formal charges. And then we're going to determine the hybridization. Now, hybridization is really about understanding the electron geometry, right? So if you have a linear electron geometry, you're going to have SP. If you have a tetrahedral electron geometry, you're going to have SP3. If you have a trigonal bipyramidal, you're going to have SP3D. Now, these ones are not options, so it's one of those three, but we got to see first what our Lewis structure looks like. And notice Chem 101 does a great job with this, where it keeps going back to Lewis structures because they really tell us how to build structures, and then that can correlate into a three-dimensional molecular structure, which becomes important as we get into molecular polarity and intermolecular forces, which is the forces between the discrete molecules of covalent bonds. So let's try this. Okay, so we got IO4, so I brings 7, oxygens bring 6, there's 4, and then you have the additional one from the minus charge. And so we have 24 plus 8 equals 32 electrons to work with. Now the I is listed first, and so I'm going to make that my central atom. I'm going to give it 4 bonds. Now, if I give each of these, there's 6 valence electrons. Right, so this is my process. I'm going to start with single bonds. See where I'm at. So that would be 8, 16, 24, 32. Right, if I check, I needed 32, so that could work. But let's look at our formal charge. Not good, not good. Right, so we don't want a +3. We don't want -1s on all of them. Now, it adds up. So we've used the right amount of electrons because our formal charge adds up to that -1, which is what it should be. So that formal charge can be another way to check if you violated the number of valence electrons that you have. It should add up to the charge of the molecule. But we don't like that. So remember, oxygens, we've seen these patterns where oxygens like 2 bonds, 2 bonds, 2 bonds. So we're going to do as many double bonds as we can. So if we take away some of these and instead make it a double bond, so now we got some zeros. We got a +1. So let's do one more. We want to get this iodine to a 0. There we go. We got 0, 0, 0, 0, and -1. We're going to have one -1 because we have a -1 overall charge. So that looks better as far as formal charge goes. A bunch of zeros and one -1 instead of a +3 and a bunch of -1s. So I'm going to go with that for my Lewis structure. Now, so the next part is, what is the hybridization? And what I see is I got no lone pairs around here. So if I had additional electrons to work with, I could have added some lone pairs, which would have adjusted it, but I didn't have any extra lone pairs. So I have 1, 2, 3, 4 electron groups, right? An electron group can be a lone pair. It can be a single bond. It can be a double bond, or it can be a triple bond. Those are all 1 electron group. So this has 4 electron groups, no lone pairs, which would be tetrahedral electron geometry, which would be an sp3 hybridization. Now you might need to look at your notes to see that correlation, that sp3. But again, the way we can see that is, maybe you don't have it down yet, but this is an s and 3 p orbitals. So 4 orbitals that central atom is evenly splitting with energy. Now, if we had 5, so if it had 5 electron groups, it would need an s, 3 p's, and 1 d. Another option is 6, which would be sp3d2, which is not given in this option. Or we could do sp2 if there's only 3 electron groups, or sp if it's linear, 2 electron groups. And so it's telling you how many s and p orbitals are of the same energy, how many have been hybridized. You don't have to have all your s and p's hybridized. Okay, let me select that. There we go.